4. Alright, a wire. Okay. A wire is stretched between two supports, and the wire is vibrating with a standing wave of a frequency of 600 hertz. That frequency is 3 times the frequency of the fundamental of the standing wave. 3 times. Is vibrating with the standing wave that has frequency 600 hertz, which is 3 times the frequency of this fundamental standing wave. Somehow I don't believe you. What is the speed v of the transverse waves of the wire? Fortunately, let's see. Oh no, we do need to know that though. Wow. Okay. Let's write on the correct surface. V is equal to F lambda. But we are told lambda is 3 times the frequency, okay? Doink, 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 doink. No, don't move it. Right, let's check the equations in the end. Okay. So we have, here's our waves here's the equation for the frequency of standing waves on a string with both ends tied down. So if we are, F is equal to this lovely stuff here. Right? Yes. So, yeah, this is just it right here. This is what we need. Fn on 2L times velocity. Basically, it says that lambda is in on 2L. So that means that this, okay. And lambda is in on 2L. Where in this particular case, n is 3, right? Yes. No. It says that this is one on lambda. Try it again. We have F is equal to n V on 2L, where in this case n is 3. And the frequency is 600 hertz. We know the L, we know the N, just find V. Let's not get fancy about it. Let's keep it simple. Let's keep it simple, stupid, right? So we have F 2L divided by N is equal to V is equal to velocity. There we are. And this 2L on N is lambda. So punch in numbers. Frequency is 600 hertz. 2L is 3.6 meters divided by 3. Okay, so that means our velocity is 200 times 3.6, 720 meters per second. Did that make sense? We'll be right with A at 720 meters per second. Do these units work right? So a hertz is a frequency is an inverse period, which means that a hertz is an inverse second. Yes, that does make sense. Or does the units make sense? A wire is stretched between two supports. The speed of the transverse wave in the wire is 900 meters per second. The frequency of the fundamental is 600 hertz. What is the length of the wire? Fundamental, transverse, stretched between, yep. Okay, so that does indeed work out the way this, it goes back to this one here. N is now equal to 1. Length of wire, okay. L is equal to NV divided by 2F. Yes. So we are told that this is 1 times the velocity of 900 meters per second divided by 2 times the frequency of 600 hertz. Hertz cancels inverse seconds. We're left with a meter. Very good. 9 divided by 2 times 6 is 0.75 meters. T is good. All right. A person is moving 20 meters relative to the ground toward a train that is moving toward her with a speed of 60 meters per second relative to the ground. Train's whistle is emitting sound waves with a frequency of 560 hertz. The speed of the sound in air is 340 meters per second. What is the frequency that is heard by the woman? Or the person? Started as a person, turned to a woman. Alright. But there's the her right here. At least he's consistent. That's nice. So we have the frequency of the listener is equal to, this is Doppler shift by the way, V plus V listener? Let me double check that. Where do you go? Okay, just make sure we didn't overshoot it. Listener on top, yes, good. V listener divided by V plus V source times the frequency of the source. You change to make sure that these the plus and minuses makes sense. If the listener is approaching the source, then we expect it to go higher. Plus makes that happen. If the source is approaching the listener, then we expect that to go lower. Therefore, this needs to be goes higher. Therefore, this needs to be a minus to make that happen. Frequency heard by observer, okay, so that is 340 plus 20 divided by 340 minus 60. And the source is 560 hertz. Given that we know it goes higher, we can immediately scratch out those there, leaving us with 640 and 720. I would expect this 640. So, nope, 720. That's pretty big jump there. You are standing at rest. A siren on a stationary fire truck emits a sound wave with wavelength 0.8 meters. The fire truck then drives rapidly away from you. While the fire truck is moving away from you, the wavelength of the sound you will observe will be okay. Well, we expect the sound to drop pitch. So V is equal to F lambda. If the frequency drops, then lambda is equal to V on F, right? If the frequency decreases, then the wavelength increases? That doesn't sound right. Lambda should be larger. Moment. Yes, that's right. That's right. If the frequency gets smaller, then lambda, wavelength, goes up. So if this goes down, then this goes up, because 1 on X does that. Does this. So it should be greater than 0.8 meters. A point source for sun emits uniform in all directions. The sun tends to see a distance of 8 meters. The source is 2 times 10 to the minus 6 watts per square meter. What is the sound intensity at a distance of 2 meters from the source? Okay, so this goes with inverse square law. So if we have so I is equal to power divided by 4 pi r square. It's the power over the area that the power has been spread. So if it is 2 times 10 minus 6 at 8 meters, then at 1/4 of the distance, right? 8 over 2. Yeah, it's a quarter. At a quarter of the distance, then we expect it to be 16 times higher. So 2 times 16 is 32 times 10 to the minus 6, also known as 3.2 times 10 to the minus 5. Not quite. It's still too warm. Speakers A and B are driven by the same amplifier and emit sound waves that are in phase and that have frequency of 85 Hertz. Speaker A has distance D to the left of speaker B, and the waves that are observed at point P, a distance of 5 meters to the right of speaker B. Speed and error is 340 meters per second. What is the smallest value D for which there is destructive interference at P? So we want destructive interference at P. That means we have destructive interference all over this distance, and so we need this here to be like so. In order for B to cancel A at any point along this direction here. What is the smallest value? So that becomes D. So D, D is equal to lambda half. But we are not given lambda, we are given F. So we have V is equal to F lambda. Therefore, lambda is equal to V on F is equal to V on 2F is equal to, punch in our numbers, it has a velocity of 340 meters per second divided by 2 times frequency of 85 Hertz. 2 meters. 2 meters exactly. Okay. This may have been skipped over in your class. However, thermal expansion is not that hard to deal with, so we shall deal with it. A steel bar is initially at a temperature of 20 degrees Celsius. Coefficient of linear expansion of steel is 1.2 times 10 minus 5 inverse Celsius square. At what temperature will the length of the bar be 0.24 times larger than the initial value? Okay. So we need thermal expansion. Where is it? There it is. So change in L is equal to alpha times L naught times the change in temperature. It just wants the proportionality of this here. So if we divide L naught to the other side, we have delta L on L, and we get a percent value. So our percent value is equal to alpha times delta T. It wants a delta L divided by L equal alpha delta T. So now we can do a delta T equal to 1 on alpha delta L L. Alpha is provided to us to be 1.2 times 10 to the minus 5 inverse Kelvin, and it wants it to be 0.24%. 0.24 times divided by 100 is 0.0024 times 1.2 e minus 5. Really? That doesn't sound right. Oh, here. Boink. Divide 1.2 e minus 5. 200 Kelvin hotter. At what temperature? That means we need to add 20 Kelvin to 20 Celsius, which puts us at 220 Celsius. We're almost there. So close. An insulated copper rod has a cross-sectional area of this much, a thermal conductivity of that much. One end of the rod is in boiling water, and the other end is in ice water. Heat conducted through the rod melts this much ice in this much time. What is the length of the rod? All right. I think, I don't remember what the symbols are. Where do you go? H, okay. So H is equal to heat moved in a certain amount of time, which in this case is equal to the amount of mass of ice melted times its latent heat of fusion divided by the amount of time taken to do so. This is equal to the thermal conductivity of the copper times its area times the change in temperature from the hot side to the cold side divided by the length in question. We should have all these numbers somewhere near at hand. I think we're missing the latent heat of fusion of water. Otherwise, we are good to go. Oh, I know what's going on here. This here. Here we are. 3.34 times 10 to the 5 joules per kilogram. 3.34 times 10 to the 5. Nope. Three 0.34 times 10 to the 5 joules per kilogram. Okay, now we have all the information we need. We can now find L. So we are told that it is 0.015 kilograms times 3.34, that's a level 4, times 10 to the 5 joules per kilogram divided by time is 600 seconds, so about 5 minutes. And this will come out to be, so let's see, kilogram cancels kilogram. Joules per second is a watt. 0.015 times 3.34 E5 divided by 600. 8.35 watts. And nope, yeah, 8.35 watts is equal to our thermal conductivity, 385 watts per meter Kelvin. Area, the area is 2 times 10 to the minus 4 square meters. And then we need temperature difference is 100 Kelvin. And then I think I got everything there except the L. So Kelvin cancels Kelvin. Watts cancels watts. Meter squared divided by meters is a simple meter. Meter over meter works out correctly. So that's 385 times 2e minus 4 times 100. 7.7. So we have that 8.35 is equal to 7.7 meters per L. Therefore, L is equal to 7.7 meters over 8.35. .922 meters. Oh, so good. Most excellent. How much heat energy must be added to 0.2 kilograms of ice so that it goes from initially minus 30 Kelvin to liquid water at plus 20 Celsius, minus 30 Celsius. We can make this work yet. Okay. So we need Q is equal to mass delta T, C delta T. C delta T. And we're also going to need some Q to melt it. And some more Q to raise its temperature even higher. So the Q in question is equal to mass times C of ice and 30 Kelvin to raise it, plus latent heat of fusion, plus C water and another 20 Kelvin to raise it even further. Okay. We already have latent heat of fusion up here, but I need the other two numbers. C ice and C water. Water is 4190. Joules per Kelvin kilogram. And sea ice is 2010 joules per kilogram Kelvin. We're told 0.02 kilograms. The sea ice, kilograms will cancel with kilograms. Inverse kilograms will cancel inverse kilograms. Kelvin will cancel with Kelvin. And leaving with joules. Sea ice is 2010 joules plus 3.34 times 10 to the 5. Yep, times 10 to the 5 joules. Oh, I missed a spot. I need the 30 in here. Plus 3.34 times 10 to the 5 plus 4190 joules 20. Calculator, tell me, what is the answer to that? 0.02 times, begin, 2010 times 30 plus 3.34 E5 plus 4190 times 20. $95.62 joules. This much. So good. That is most excellent. I saw a piece of metal with mass of 0.2 kilos and initial temperature of 400 Celsius is placed in 0.3 kilograms of water that is initially a temperature of 30 Celsius. The water is in a container of negligible mass and no heat is lost to its surroundings. The final temperature of the metal and water is 50 Celsius. What is the specific heat of the metal? Okay. So we have two Q's here that we're going to add together. So we have mass of the water is water initially at 30 Celsius and it goes up to 50 Celsius. Okay. C water delta T plus M methyl C methyl delta T is equal to 0. No heat leaves or enters. Let's see here. We'll go ahead and punch in some numbers here. Mass of the water is, where do you go? 0.2 kilograms. Seawater kilograms. Seawater is 4190 joules per kilogram Kelvin. The temperature rises 20 Kelvin. Kelvin cancels Kelvin. Kilogram cancels kilogram. We have a joule. Equals minus mass of the metal, which is divided by, I buggered that up. That's 0.3 there. Minus 0.2 kilos here. Sea ice, sea metal that we are looking for. And its temperature is minus 350 Kelvin. So then we have 0.3 times 4190 joules times 20 divided by this minus, we cancel that minus, 0.2 kilograms, 350 Kelvin. And this is the C at the middle. 0.3 times 4190 times 20 divide by, begin, 0.2 times 350. 359 joules per kilogram Kelvin. Okay. All right, end of that page. Next page. Okay, now we're getting to thermodynamic processes. You may or may not have seen these in your class because the semester has been weird, because Texas can't figure out how to keep its power on. Oh, privatization, yay. Sometimes it works and sometimes it doesn't, and that's not one of them. A large cylinder tank contains 0.8 cubic meters of an ideal gas at 27 Celsius and a pressure of 1.5 times 10 to the 5 pascals. What is the gas pressure if the temperature of the gas is increased to 227 Celsius and volume is unchanged? Okay. This appears to be an ideal gas law to me, right? PV is equal to NKT. N will be unchanged. V is unchanged. P will change, but with temperature. So we need to get P and temperature together. So we end up with P over T is equal to NK on V. This is constant. So now we have P initial on T initial is equal to P final divided by T final. So we are told pressure. So yeah, this is an ideal gas law. So this is all fine here, all fine and dandy. So we actually need to convert our temperatures to Kelvin. That would be 273.15. How would you do that? 273. I'll bet you that's 300. 273.15 plus 27 is 300. Yep. Okay, nice round numbers, as I would expect from Dr. Ford. 1.5 times 10 to the 5 pascals divided by 300 Kelvin is equal to the pressure final that we are unfamiliar with. Multiply that by T final up 200, so this is 500 Kelvin. 100 Kelvin cancels 100 Kelvin. And so we end up with 5/3 of the initial pressure. 1.5 times 5/3 is 2.5. 2.5 times 10 stuff times 10 to the 5 pascals. 2.5 times 10 to the 5 pascals. A mixture, okay, yep, more, okay, this is probably another ideal gas problem here, some sort or another. A mixture of helium gas, M equals 4 grams per mole, and neon gas, M equals 20 grams per mole, is in thermal equilibrium at a temperature of 300 Kelvin. Treated gas is ideal. So these are monatomic gases because helium and neon do not bind to anything. So as they don't bind to anything, they are monatomic. Which of the following statements is true? Average kinetic energy of helium is larger than that for neon. Average kinetic energy for helium is smaller or the same. Alright. Kinetic energy average. Where is it? Here we are. Nope. Here we are. Kinetic energy average is equal to 1/2 mv squared is equal to 3/2 kT. Oh. So kinetic energy is equal to 3/2 kT. Kinetic energy is equal to 3/2 kT. Oh, mass of these two things has nothing to do with this equation at all. Therefore, kinetic energy is equal. Five moles of monatomic gas undergo an expansion at constant pressure and temperature. Oh, and the temperature increases from 200 Kelvin to 300 Kelvin. What is the change in the internal energy of the gas? Okay. Okay. So internal energy I believe that equation is given to us. There it is. Nope, that's not it. So we're looking for a change in delta U. That's our internal energy for this gas here. And we have a Q, which is given here, and work, which is probably should be either this one or that one, or neither. So we have change in U is what it's looking for, is equal to due to monatomic gas undergoes expansion constant pressure and temperature increases. Constant pressure. Okay, so P is equal to delta V. Oh. This equation is not on the equation sheet for reasons I don't quite understand. Scratch this out. C, where'd you go? It's basically Q here. In C delta T. Scratch that out. Delta U is equal to in C delta T. And the question is it constant, is it P or V? And we are at constant pressure, so this is CP. CP for monatomic gas is, let's see here. Oh, okay. Here we are, CP, 5 R halves. So then we have in 5 halves R delta T. In, we are told, is 5 moles. 5 halves R. Where's R? It's a constant, so it has to be given. Where is the ideal gas constant? It should be given. There it is. 8314. 8314. Where we go? Joules per mole Kelvin. Joules per mole Kelvin. Delta T is 100. Kelvin cancels Kelvin, mole cancels mole, and we're left with joules. 5 times 5 halves times 8.314 times 100. And this is 10,392.5 joules. And to round it to 3 significant figures, 10,400 joules, or 10.4 kilojoules. That is excellent. Still good. I'm getting cold though. Biscuit eater. I did do that wrong, right? 5 moles monatomic gas and consequences change in internal energy. Internal energy is always blasted to little bits. In CV, doesn't matter if it's constant pressure or not, which means this is 3/5, which means that this number is, that this is 3/5, and this is something else. Blast it to little bits. That's no bueno. 3/5, this is probably here, yeah? Yeah. Yeah. Yep, surprise. So this is 6235. 6235.5 joules, which means that this is not the answer, and this is. That's fine. With what tension must a rope with length 2 meters and mass of 0.08 kilograms be stretched for transverse waves of frequency 60 Hz to have wavelength of 1/2 meter? Okay. V is equal to F lambda is equal to the square root of tension divided by mu. Let's double check that. ft. Yep. Yep. Good. Indeed. Do f lambda mu. What are we looking for? We're looking for tension, right? Yes. And mu is the linear density, so it is mass divided by length. Okay. So let's go ahead and square both sides and get mu by itself. No, get T by itself. So tension is equal to F square lambda square mu, or F square lambda, that's terrible, lambda squared mass divided by length. Alright. So now we put in all the numbers. 60 hertz squared, length of 1/2 meter squared, mass of 0.08 kilogram. Way off to the side. Kilograms divided by a length of 2 meters. All right. Okay. Let's take care of the units afterwards. So 60 squared times 1/2 squared times 0.08 divided by 2 is 36. 36, probably newtons, but let's check. So that's a hertz is an inverse second, so that's a seconds squared. We have a meter squared on top, a meter on the bottom, and a kilogram on top. Meters cancels one of those meters there, and we are left with 36 kilogram meter per second squared, better known as 36 newtons. Well, more simply known as. Yeah, it works. All right. Okay. We're definitely going to need a second cup of tea for the final exam here. That's for certain. A quantity of ideal gas undergoes adiabatic, Q equals 0, compression in which the volume of gas decreases. Which of the following statements is correct? Okay, adiabatic compression. The adiabatic equations are down here at the bottom. What do you want to know? It wants to know about temperature, and we are given volume. Temperature and volume. So T V to a number. We're told that T V to the gamma minus 1. Yes. To the gamma minus 1 is constant. Okay. So that means that T final is equal to T initial, V initial over V final to the gamma minus 1. We are told that this is monatomic. We are not told. Okay. So we need to determine if this is positive or negative. Gamma. Let's see here. Gamma. We are told gamma. Where is gamma? I thought gamma was given, or sort of given. There should be an equation for gamma. Here it is. CP on CV. Right. Okay. CP on CV. So that means that it is CV plus R on CV. So gamma is CV plus R on CV. So this should be, so this becomes R on CV plus 1 minus 1. So R is positive, CV is positive, therefore this is also positive. So our power is positive, and so we have an increasing value. You're told that it compresses so the final volume is smaller. So this number here is greater than 1, which means our T final is greater than T initial. Temperature increases. How much? Don't know. We're not even given enough information for that anyways. Six moles of monatomic ideal gas undergo an expansion at constant pressure. The initial temperature of the gas is 150 Kelvin and final temperature is 350 Kelvin. What is the magnitude of the work done by the gas in the process? Okay. So delta U is equal to NCP delta T, which is equal to Q minus work. Magnitude of work done in the process. Oh, right. That's not correct. This is NCV delta T, and Q is NCP delta T minus work. So that means the work is equal to N CV minus CP delta T. CP moved to that side there. Minus those over here still. Okay. So that the work is equal to NR delta T. There we go. Okay. So it doesn't actually matter if it's monatomic or not. It's always going to be the same. So N is 6 moles. R is 8314. 14 decimal goes there. Joules per mole. Kelvin? Kelvin. And we're told that it increases 200 Kelvin. Yes. Make sure you got the right R. Where'd you go? 8314. 8314. Yes, good. 6 times 88.314 times 200. 99.76.8 joules. That works out to this one right here. The surface of our sun has a temperature of 5800 Kelvin and an emissivity of 1 because it's plasma, and plasma, despite being very bright, is in fact a black body. The sun is radiating energy at a rate of 3.9 times 10 to the 26 joules per second. Using this information, calculate the diameter of the sun. Area of a circle, pi r squared, and the surface area of a sphere is 4 pi r squared. The volume of a sphere is 4/3 pi r cube. That is way too much information, I think. All right. So h, we are given, is equal to this one here. This is the this is h for radiating heat away, or absorbing heat by radiation. So that is AE sigma T to the 4. AE sigma T to the 4. Better known as 4 pi r squared. E is 1. Sigma is given as a constant. And temperature is 5800 Kelvin to the 4th. 4 pi diameter. Oh, for love Pete, really diameter? Good gravy. Watch out for that. 3.9 times 10 to the 26 joules is over. No, let's not punch in numbers too early. We need the radius. Radius squared is equal to 4 pi sigma T to the 4 under h. So we square root that and double it. That's getting cold. Let me finish that. This exam is almost done. 3 more questions. 4 more questions. Alright. So D is 2 square roots h over 4 pi sigma T to the 4. Punch in numbers. Sigma, Stefan Boltzmann constant, 5.67 times 10 to the minus 5. 5.67 times 10 to the minus 5 in appropriate units. And I think everything else is given on this page. 2 square root h, 3.9 times 10 to the 26, divide by 4 pi sigma 5.67 E minus 5 times temperature of 5800 to the 4th. Is a really big number because it's in meters. Why do you do this? This doesn't make any sense. Whatever, my calculator doesn't help me either. Anyways. 4, 3, 9, 8, 5, 5, 3, 2.15 meters. 1, 2, 3, 4, 5, 6, 7, 8. Really? End, divide by 10 to the 9. Uh-oh. That's not good. 0.0439 times 10, whatever, times 10 to the 8. Oh, no, that's times 10 to the 9 meters. Interesting, says I. Let me double check, make sure I told the calculator things correctly. Okay, so area is 4 pi r squared. And what's the diameter? Okay, 4 pi r squared. Sigma, emissivity of 1. Okay. T to the 4th. Okay. Solve that for r. So we get that h is over 4 pi sigma t to the 4 square root it, and then double it to get the diameter. Diameter is therefore 2 times the square root of h over 4 pi sigma t to the fourth. Okay. Times 10 to the minus 5. 567 times 10 to the minus 5. 58. Yeah. Times 10 to the 9. Okay. Sigma 567 times 10 to the 8. Oops. That would do it. There we go. It always helps to get the right number in there. Times 10 to the 8. That will change a whole lot. That'll change things. So let's go ahead and put that number in there. Where's my Control B? Shift B. R. N. One 3,9,0,9,4,4,6,5,7 meters. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1.39 times 10 to the 9 meters. There we go. That's better. Hoy. Always write things Always write things down correctly or you're going to get the wrong answer. Alright, last page. Alright, there is 0.04 kilograms of ice of insulated containing neutral mass. Initial temperature is 0. What mass of water at 80 Celsius must be poured into the container so that the final temperature is 50 Celsius if no heat is lost to the surroundings. Alright. So this is more calorimetry. So first we need to melt the ice. Then we need to raise its temperature with specific heat up a certain amount. And we are adding to that some amount of water, the same as C, and its own change in temperature, such that no heat escapes. So we have 0.04 kilograms of ice is latent heat of fusion is 3.34 times 10 to the 5. 3.34 times 10 to the 5 plus specific heat of water is being 4190, double check, 4190 times the C, C, times its change in temperature is 50 Celsius. Or 50 Kelvin, in case may be, plus some mass of water. It has a C of 4190, and it has a temperature decrease of it has a temperature change of minus 30 Kelvin equals 0. Okay, so then we scratch this, we set equal, and then we divide this to the other side. 4190, 30. This minus cancels with being brought to the other side. And we get a mass of water. 0.04, 3.34 E5 plus 4190 times 50 divided by, begin, 4190 times 30, end and execute. 0.173 kilograms. A quantity of monatomic ideal gas is at an initial temperature of 300 Kelvin undergoes expansion at constant pressure. Okay, so CP, if it needs to be done. And the gas does 200 joules of work. In this process, how much heat entered or left the gas? Okay, we don't need that. Delta U is equal to Q minus W. Okay, and this is equal to NCV delta P. Q is therefore equal to NCV delta T plus work. We have the work, we have the change in of temperature, and quantity. A quantity, he says. The work is equal to NR delta T, as I showed in a previous example. So we can find NR by doing this. So we have that work over change in temperature is equal to NR is equal to 2/3. 2/3 of proper units, which would be that would be a joule per Kelvin. Okay. Do you want to do this? Let's see here. Q, how much heat? Yeah, we have to do it this way, I believe. NR, right? Joule per Kelvin. Yeah. So this becomes CV is 3/2 R, right? 3/2. Yeah, NR. Delta T plus the work. So Q is let's see where we go. 3/2. We're told the NR. We figure out the NR is, so 3/2. NR is 2/3, and then we have the delta T, which is that's joules per Kelvin, and then that's initial temperature 300 Kelvin. Nope, no, back up. And does 200 joules of work. Good gravy. Good gravy. Yeah, no, we're still fine. Delta T plus the work, which is in R. Delta T. I think I went about this just about the wrongish way. We'll come back to this. I think I need a. We'll come back to that. We'll come back to that one. A quantity of monatomic ideal gas undergoes a process in which the internal energy of the gas is increased by 400 joules and 600 joules of heat enters the gas. In this process, does the volume of the gas increase, decrease, or stay the same? Okay. Boy. Let's see here. Internal energy. Delta U is equal to 400 joules. Q is equal to 600 joules, which means work is 200 joules. Work done by it is 200 joules. In quantum monatomic gas undergoes internal so the temperature, because this is equal to NCV delta T, means that T had to increase. Delta T had to go up, but I don't think that's what we need to be concerned about. Yeah. Because of its NCV, this is not equal to NCV. This is not equal to NCV delta T. So that means that V is not constant. V is not constant. Okay, so I have eliminated that it stays the same. Okay. Does it increase? Temperature has increased. Most likely, that means that the volume has also increased. Let's have a look. See, because I believe U has some constants around here. I'm not seeing it. That's most unfortunate. So I would say that volume increases given that the temperature has increased, and that volume is in fact not constant. Let me find out if that is correct. That would be most weird if it was not, if I was not correct. This is for, not that one. Nope, don't do that either. Stream Manager 1. Okay, whatever. So where is I? Let's hear. That's right. This is exam 4. Let's see here. What am I looking for? Exam 4. Exam 4, 20 with answers. Preview that. Ta-da! That's right. It does increase. Okay. I was quick about that. Okay. Okay. Now, I'm going to come back and try this one again. A quantity of monoatomic gas at initial temperature 300 Kelvin undergoes an expansion at constant pressure and does 200 joules of work. Q is NCP delta T. Okay. Work, and because this is monatomic, that means that is 5/2 in R delta T. The work is in R delta T. In this process, how much heat has entered or left the gas? Right. No, let's not overcomplicate things. 5/2 in RT, in R delta T, in R delta T. This is 5/2 work. So that's 5/2 of 200 joules. So we don't need to know what temperature it's at. We just need to know this. And so that's 500. That's come on, really? 5 halves, 200 joules is equal to 500 joules is equal to Q. So that can go away, that can go away. So did it come into or out of the gas? Gas does 200 joules of work. So that should be coming out of the gas. That should be energy coming out of the gas, yes? Uh-oh. Nope. It's going into the gas. That's work coming out. Well, yeah. So the problem that I'm having is sign convention. So delta U is equal to Q minus work. And so this is heat going in, and this is work done. So work out. So if we have 200 joules of work going out, then Q going in. So basically I have to trust that the sign conventions will actually work out correctly. And so we end up with that if work going out is positive, then heat going in in this particular situation must also therefore be positive. And so it's 500 joules going in rather than 500 joules going out. All right. Well, that is the end of exam 4.